on that object, the optical element, and creates a new image. And this formula tells you where these relative images are with respect to what's called the focal length, f. Now, the only really tricky part of this is that these s's, the distances, and the f have numerical signs, plus and minus. And it's a heck of a job, unless you've got very good memory, to remember all the different possible cases of when is one s positive, when is s prime negative, when is f negative. So I'll tell you a very quick, simple way of remembering it. I'll just erase this now. What I would say is set up the most obvious case, and the most obvious case, everything is positive. And if it isn't the obvious case, then the thing is negative. The most obvious case, if you have a lens, when you think of a lens, you think of that. In fact, the word lens is the same word that comes from lentil. You know, you've seen lentils? They're shaped like that. So if you think of a thing as lenticular, like a lentil. So here's a lentil. And so that's, I mean, most people, if you say lens, they don't think this. They think this. So think the most obvious thing. And the most obvious situation is that you have an object in front, a person, a thing, and that you have an image behind. If you have that, everything is positive. If you have anything more peculiar than that, then it's negative. For example, if in this case, for some reason, so this is the object, and that was the image, and that is I like to call it the standard case. And everything is positive. Plus, this is positive, this is positive, this is positive. Everything's positive, no problem. Okay, if it should turn out that you have this situation, you have your object, and it should turn out that your image is over here, that's negative. It's not the standard case. Object in front, lens over here, image over here, this guy is in the wrong place, is negative. Yeah. Also, if suddenly you should see a lens that doesn't look like a lentil, it's negative. So if I see something like this, I say that's not my standard case, this is negative. Its f will be negative. This is providing me an s, f, and s prime. If they're in that order and it's a lentil, they're all positive. If you see something like this, an object, and a non-lentil, and an image, this guy would be negative, this guy would be positive because he's in the normal position, and it'll turn out that with a thing like this, you'll never get an image over here. You'll always get an image over here. You'll always get an image over, so that'll be negative also, because he's in the wrong place. That's all you have to remember. Same is true with mirrors. When you think of a mirror, what do you think of? Well, I think something like this, frankly. Right? Shiny surface over here. Actually, the more natural would be a plane mirror, like the mirror in your bathroom. But if you would think of a curved mirror, that's what I would think of first off. And everything, and then the standard case is the object over here, the image over here on this side of the mirror, and that's all positive. Object, image, shape here, that's all positive. So you have s, s prime, and f, all positive in the standard case. If anything is different from that, for example, it could happen that s prime is over here. If it should turn out that you're suddenly getting an s prime on the other side of the mirror, that's negative. So you have to remember. Just remember the standard case, and if anything comes out wrong, peculiar, it's the wrong side, the opposite side. Or you could have a mirror that looks like this, so-called convex mirror. Here, it's not like that, so this would be a negative mirror. And it always will create an image on this side. No, it'll always create an image on this side. So that will be negative too. Typically your object will be outside the mirror because otherwise something's going to break if you go inside the mirror. Unless you're Alice in Wonderland or something. So that's it. That's all you have to remember. To remember the standard cases. Actually, it doesn't have to be. You can get some cases where the object is behind a lens because it's coming from somewhere else. We'll get to that maybe with optical instruments where you're having compound lenses. So typically, in a normal case, the object is in front of the lens of the mirror. But you could have yet another object over here, a lens of some sort, which creates an image over here, and that is the object for another lens. So, and that'll be behind this, and it'll be negative for this one. So that is conceivable. But in a single lens, you can always set it up so that the object is in front of the lens. We'll leave that for compound things like microscopes. That's yet tomorrow, next week's chapter. Okay, now the importance of focal points I try to emphasize, and the only thing that you really have to know is the distances, s and s prime, are adjustable. You can put the thing anywhere you like. The one thing that is determined by the geometry of the optical element is its focal length. And there are two different formulas which actually turn out to be rather similar, in fact, to each other. For the focal length of a lens, it's given by this. Again, there are some tricky points here. The only tricky point, though, is that these have signs. As you might expect, and I can show it to you, the focal length is given by n minus 1, 1 over r1 minus 1 over r2. And again, the r's have signs. But again, we just go with a simple convention. If it's convex toward the object, we give that a positive sign. If it's convex away from the object, in other words, this material like this, and you have your r like r2, say, if it's convex away from the object, we give that a negative sign. So again, it's kind of the simplest, most obvious thing is called positive, and the less obvious is called negative. So that's it. That's all you have to remember. Okay, and I think I put this in here. There's a simple rule. The standard case of both the lenses and mirrors are those. And the focal length, it turns out, of a spherical mirror is simply half the radius of that surface, which I talked about, I think, last time. And there are different kinds of mirrors. You have, of course, the plane mirror, like the bathroom mirror. You have the concave mirror, which ladies may know as a makeup mirror, and the guys know as shaving mirrors, where you are concave mirrors, and if you get close enough, you will see yourself magnified. Then you have a convex mirror, which is the lower one, which is the mirror familiar to you. It's your side view mirror in your car. The side view mirror of your car is that kind of a mirror because what you're trying to do is see a wide angle, and you always want to see the things right side up. It would be very distracting if you looked in the mirror and suddenly you saw things inverted, you know. And also you want to have a broad view. So it turns out that the side view mirror is a convex mirror, and it reduces the size of things, but at least it keeps them upright, which is a blessing. Now the way we solve problems is by knowing certain special lines with respect to these optical elements. This is really a rather longer story than I was hoping to get into. Well, we just have to do it, though. The point is that there are special lines, and if you know 3 lines, in fact, if you know 2 lines, you can get a point. So you can find out where things focus. For example, we know if you have a lens like this, if you send a ray through the center of the lens is pretty much plate glass, right? It's not angled. So the light will go through straight. So that's one nice line. Then we have, if you send in a light parallel but not through the center, that light will refract toward, and when it comes here, it will refract away, and it will bend, and it will pass through the focal point at the focal length. So a parallel beam goes through the focal point, and that's enough to determine where the focal point is. You could do some others. Let's see what we do. Well, you can do one down here, of course. It's the same story. It will pass through here. A parallel beam will pass through the focal point, or a light passing through the focal point, if I can get that angle right. Oh, yeah. Will go parallel. So I should do that one with a different color, perhaps. Again, it's the same idea. The light is reversible. If it passes through the focal point, it will go parallel. If it goes parallel, it will pass through the focal point. So depending on what rays you have available to you, if you have 2 or 3 of them, 2 is enough, you can locate the image. And we have the idea of magnification. The relative height of the image over the object will be the relative height, relative distances with a minus sign. Again, the signs come in because it's possible for the image to be inverted. The thing I did want to show you before time runs out is this idea of real and virtual images. You can talk about them, but it's really fun to see exactly what they are. And for example, here's a demonstration. I don't know what you can see. Do you see a lamp glowing? Okay, and it looks like it's over here. Everybody agree? Abracadabra, hocus pocus, hocus pocus. Ta-da! Hocus pocus. What's going on here? It's just smoke and mirrors. This actually is glass. It reflects somewhat, so it's a mirror. Actually, the lamp is over here, and the light is coming, and it's spreading out. It's coming this way, and it's spreading out to you, and it looks like it's coming from here. Isn't that unbelievable? So I can put it back in or not, as you wish. I can put it over here, and the light goes on. So that's a virtual image because it looks like it's coming from, but there's no light here. So there's a virtual image. Can you see it even if over there? Okay. So that's a cute one. Now, on your way out, we have only 5 minutes. Please do stop and see this one. This is a little bit different. I should maybe explain it a little bit. What it is this is one of these concave mirrors, which let's do the geometry on this guy. It's maybe worthwhile. Yes. Okay. So the picture here is I have this giant mirror here. It has a radius about yay. Okay. So it has a focal point about here. If I put an object at the focal point, and I use my formula, 1 over s plus 1 over s prime equals 1 over f, which is the formula that applies to lenses and mirrors. If I put the, let's see, I may want to put this at the, let's see, when would I get an image, this image, I want the image magnification to be 1. Because I want to see what's going on here. Some of you have seen this already. There's a bunch of false flowers hanging from here. And I want an image of that, same size, to appear here. So I want it to be inverted and the same size. So let me see what I have to do here. I want the magnification to be 1. I want the bunch of flowers to be reproduced, but right side up. So there's actually real flowers here, and I want them to appear here. So magnification is 1, and that's s prime minus over s. I want that to be 1, so I have to get s equal to s prime. That has to be 1. So I have 1 over s, that's the object distance, plus 1 over s prime, that's 2 of them, equal to 1 over f. So I have to make s equal to 2f, which is the radius of the sphere. So what I should do is put the bunch of flowers at the radius of the sphere. Here's my flowers. And in principle, the light will come from this point. It will reflect, and I'll get light even something like this. So the parallel beam will pass through f. You see, so all the light from this point. See, here's my 2 rays. Here's my 2 special rays. One of which, hits here. Oh, that's another special ray. Because it hits a perpendicular, the radius like this. The angle of incidence is equal to the angle of reflection. So a special ray will come. That's all right. Welcome. So that's one set of rays. The other one is the one that's going parallel to the mirror. It'll pass through the focal point. So all the rays coming from, and every one in between, will end up at this focal point. So a point on this flower will end up as an image here. And the rays, in fact, continue out. So in other words, they're coming in all directions. And they will all come out, and they'll all come out. So this acts like as though the same way this does. So that's a real image, because all the light is coming out of that point, just like it's coming out of this point. That's a real image. Because the light actually started here and is going out, so that's a real image. You could project it on a screen, because the light is coming out of that point, or it's going to hit that point. So let me turn this guy off. Okay, so time is, that's up. So that's the theory of this, and it's quite a striking illusion. If you haven't already seen it, please do. And then you'll come to be amazed that that's exactly what's happening here.